Course description and units. Probability means chance or possibility of occurring event. Probability gives a numerical measure of this chance or possibility. The collection of all possible outcomes of a random experiment is called sample space, and a subset of sample space is called an event. Using the formula of mathematical definition of probability, we calculate probability of different events for different random experiments. Concept and applications of addition law, conditional probability and multiplication law are very important in solving practical business situations. A random variable is a function that associates a real number with each element in a sample space. A probability distribution is a statistical function that describes all the possible values of a random variable x and its corresponding probabilities that x can take within a given range. Probability distribution is of two types, discrete and continuous. Binomial and Poisson are examples of discrete, and normal is an example of continuous probability distributions, which have many practical applications. Unit 1 Objectives. Unit 2 Objectives. On completion of this course, you will be able to develop an understanding of the theory of probability and rules of probability. Apply probability rules and concepts within a practical and business context. Demonstrate knowledge of the importance of probability in practical situation. Duration, 1 hour. Introduction. To understand the concept of probability, first we need to understand the concepts of factorial, permutation and combination. Probability. Factorial. Permutation and combination. Factorial. The product of the first n natural numbers is called factorial n, and is denoted by n. Using this result and splitting further we get permutation and combination. Permutation means arrangement. Suppose there are n objects and r places. Number of ways we arrange our objects in n places is called permutation. Permutation is the arrangement of objects in which order is priority. Combination is the arrangement of objects in which order is irrelevant. Combination means selection. Suppose there are n objects. Number of ways we select our objects from it where order is not important is called combination. The notation for permutation is P of n, r or npr, which is the number of permutations of n things if only r are selected. The notation for combination is C of n, r or ncr, which is the number of combinations or selections of n things if only r are selected. If there are 3 things A, B and C, then permutations of 3 things taken 2 at a time is denoted by P of 3, 2 or 3p2. It is given by A, B, A, C, B, C, B, A, C, A, C, B. We get, in general, the number of permutations of n things taken r at a time is given by P of n, r equal to npr equal to. If there are 3 things A, B and C, then combination of these 3 things taken 2 at a time is denoted by 3c2, and is given by A, B, A, C, B, C. So, in general, NCR equal to. Note, permutation and combination are related to each other by formula P of n, r equal to RC of n, r. Illustration, probability. 1. P11, 4 equal to 11 P4 equal to 2. P8, 5 equal to 8 P5 equal to 3 cards are to be sent to 4 persons, and how many ways this can be done? Solution, we have to find number of permutations of 4 objects out of 6 objects. That is 5. In how many ways 2 pens can be selected from 6 pens? Solution, 2 pens can be selected from 6 pens in 6c2 ways. 6. In how many ways 4 cards can be chosen from a pack of 52 cards? Solution, 4 cards can be chosen from a pack of 52 cards in 52c4 ways. 7. From a group of 7 boys and 6 girls, 3 boys and 4 girls is to be selected. In how many ways this can be done? Solution: 3 boys can be selected from 7 boys in 7C3 ways. 4 girls can be selected from 6 girls in 6C4 ways. 3 boys and 4 girls can be selected in 7C3, 6C4 equal to 35, 15 equal to 525 ways. 3 boys and 4 girls can be selected in 7C3, 6C4 equal to 35, 15 equal to 525 ways. Some important results of set theory. Set theory is a branch of mathematical logic that studies sets, which informally are collections of objects or things of similar type. Although any type of object can be collected into a set, set theory is applied most often to objects that are relevant to mathematics. Sets are usually denoted by A, B, C. The following are some examples of sets. A equal to the set of integers equal to 1, 2, 3, 4. B equal to the set of vowels equal to A, E, I, O, U. C equal to the set of days in the week. Equal to Sunday, Monday, Tuesday, Wednesday, Thursday, Friday, Saturday. The objects in the set are called elements or members of the set. X belongs to A implies X is an element of the set A. X not belongs to A implies X is not an element of the set A. Union. The union of the set A and the set B is the set that contains all the elements that belong to A or to B. Written A union B intersection. The intersection of the set A and the set B is the set that contains all the elements that belong to A and B both, written as A intersect B. Complementary set. The elements of the universal set S which do not belong to the subset A, forms a set, which is called complement of A, and is denoted by AC or A or A. Universal and empty set. In a set theory, a universal set is a set which contains all objects, including itself. Note, the complement of universal set is called empty set, or null set. Universal set is denoted by S and empty set is phi. More information. Probability means possibility or chance. We are certain about rising of the sun every day, about there are 7 days in a week, etc. However, there are many things where we are not sure about the occurrence or the outcome of the incident. In those cases we use the words probably or likely or possibly. For example, probably it will rain tonight, it is quite likely that there will be a good yield of crop this year, and so on. But the terms probably, quite likely are all relative terms of uncertainty. Probability is a numerical measure of uncertainty, a number that conveys the strength of our belief in the occurrence of an uncertain event. The theory of probability was largely developed by European mathematicians such as Galileo, Pascal and others. To find a measure for probability it is necessary to have the concept of few terms which we discussed below. Random experiment or trial. An operation or experiment conducted under identical conditions, and which has a number of possible outcomes, is called random experiment or trial. Example: tossing a coin, throwing a dice, selecting a card from a pack of cards. Sample space. Collection of all possible outcomes of a random experiment is called sample space. In other words, set of all possible outcomes of a random experiment is called sample space. The elements of the sample space are called sample points. Sample space is denoted by S. The number of sample points in a sample space of random experiment is denoted by N of S or M. Example: in an experiment of throwing a coin, sample space S equal to H, T. In this example N of S equal to M equal to 2. Discrete sample space. A sample space containing finite or countably infinite number of points is called a discrete sample space. Example: if the random experiment is throwing a dice, sample space equal to S equal to 1, 2, 3, 4, 5, 6. Continuous sample space. A sample space containing uncountable sample points is called a continuous sample space. Example: set of all rational numbers. Event. A part of sample space or any subset of the sample space S is called an event. If S is a sample space and A is a subset of S, then A is called an event. Example, in an experiment of throwing dice where S equal to 1, 2, 3, 4, 5, 6, the event of getting odd numbers is A equal to 1, 3, 5 type of events. Certain events. Impossible events. Equally likely events. Exhaustive events. Complementary event. Certain events. If sample points in an event are same as sample points in sample space of that random experiment, then the event is called a certain event. Example, Sunday will come after Saturday is a certain event. Getting any number between 1 to 6 on a dice is a certain event. Impossible events. An event which never occurs, or which has no favorable outcomes is called an impossible event. In other words, the event corresponding to the set phi is called an impossible event. Example, getting a number 7 on a dice is an impossible event. Here, A intersect of B equal to phi, A intersect of C equal to 3, B intersect of C equal to 3, so A and B are mutually exclusive events. But A and C and B and C are not mutually exclusive events. Impossible events. An event which never occurs, or which has no favorable outcomes is called an impossible event. In other words, the event corresponding to the set phi is called an impossible event. Example, getting a number 7 on a dice is an impossible event. Here, A intersect of B equal to phi, A intersect of C equal to 3, B intersect of C equal to 3, so A and B are mutually exclusive events, but A and C and B and C are not mutually exclusive events. Equally likely events. Events are said to be equally likely if they have equal choice to occur. In other words, outcomes of a trial are said to be equally likely if taking into consideration all relevant evidence, there is no reason to prefer one with respect to other. Example, in throwing a dice all the 6 faces are equally likely to occur. Exhaustive events. If the sample points of the events taken together constitute the sample space of the random experiment, the events are called exhaustive events. If A and B are exhaustive events of sample space S, then A union B equal to S. Example, let us consider a random experiment of throwing a dice. S equal to 1, 2, 3, 4, 5, 6. A equal to event of even numbers equal to 2, 4, 6. B equal to event of odd numbers equal to 1, 3, 5. C equal to event of multiple of 3 equal to 3, 6. Here AUB equal to 1, 2, 3, 4, 5, 6 equal to S. Here A and B are called exhaustive events. A union C equal to 2, 3, 4, 6 S, so A and C are not exhaustive events. B union C equal to 1, 3, 5, 6 S, so B and C are not exhaustive events. Complementary event. If A is an event in sample space S, then the non-occurrence event of A is called complementary event of A. Two events A and B are called complementary events, if A and B exhaustive as well as mutually exclusive events. In other words, A and B are called complementary events, if A union B equal to S and A intersect of B equal to phi. Complementary event of A is denoted by AC, A or A. AC equal to A equal to A equal to S minus A. Example, let us consider a random experiment of throwing a dice. S equal to 1, 2, 3, 4, 5, 6. A equal to event of even numbers equal to 2, 4, 6. AC equal to A equal to A equal to S minus A equal to 1, 2, 3, 4, 5, 6 minus 2, 4, 6 equal to 1, 3, 5. As A union AC equal to S and A intersect AC equal to phi, AC and AC are complementary events. Mathematical and axiomatic definition of probability. If the sample space S of a random experiment consists of n equally likely, exhaustive and mutually exclusive sample points and m of them are favorable to an event A, then the probability of event A is given by P of A, equal to m by n, number of sample point in A by number of sample point in S, equal to n of A by n of S. Note, 0 less than equal to m less than equal to n. Limitations of mathematical probability. If the various outcomes of the trial are not equally likely. If the exhaustive number of outcomes in a trial is infinite, that is, if n tends to infinity, probability of that event can't be defined. To overcome the limitations of mathematical probability, one more definition can be used which is based on set operations, which is called axiomatic definition of probability. Axiomatic definition of probability. Let S be a sample space, and let A be the set of events. Let P be a real-valued function net on A. Then P is a probability set function, if P satisfies the following three conditions. P of A greater than equal to 0, for all A implies SP of S equal to 1. If n is a sequence of events in B and A m intersect A n equal to 5 for all m, n, then Illustration 1. 1. Write the sample space in each of the experiments. A 3 coins are tossed simultaneously. B. 2 fair dice are rolled simultaneously. C. A coin and a dice are thrown simultaneously. Solution. Illustration 2. 2. 2 unbiased dice are thrown. Find the probability that 1. Both the dice show same number. 2. Second dice shows number 1. 3. The total number on the 2 dice is 9. Solution. 1. A equal to event that both the dice show same number. Equal to 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6. Illustration 3. 3. A box contains 20 tickets numbered from 1 to 20. A ticket is drawn randomly from the box. Find the probability that the number on the ticket is 1. Divisible by 5. 2. Not divisible by 2. 3. Divisible by 3 and 4. 4. Divisible by 3 or 4. Solution. S equal to 1, 2, 3, to 20, n of S equal to m equal to 20. 1. A equal to event that the number is divisible by 5. A equal to 5, 10, 15, 20. 2. B equal to not divisible by 2. B equal to 1, 3, 5, 7, 9, 11, 13, 15, 17, 19. 3. C equal to event that the number is divisible by 3 and 4. C equal to 12. 4. D equal to event that the number is divisible by 3 or 4. D equal to 3, 4. Illustration 4. 4. 6 magazines are placed at random in a shelf. Find probability that a particular pair of magazines shall be 1. Always together. 2. Never together. Solution. 1. Consider it a single magazine. Thus now we have 6 minus 1 equal to 5 magazines, which can be arranged in factorial of 5 equal to 5 into 4 into 3 into 2 into 1 equal to 120 ways. Equal to 5 into 4 into 3 into 2 into 1 equal to 120 ways. The 2 magazines, which is considered as a single magazine, can be arranged among themselves in factorial of 2 equal to 2 ways. So, the favorable number of cases equal to 120 into 2 equal to 240. Total equal to factorial of 6 equal to 720. Equal to 720 p equal to 240 by 720 equal to 0.3333. 2. Total number of arrangements where the pair of magazines will never be together. Equal to total number of arrangements minus total number of arrangements where the pair of magazines are never together equal to factorial of 6 minus 240 equal to 720 minus 240 equal to 480. So, the favorable number of cases equal to 480 total number of cases equal to factorial of 6 equal to 720 p equal to 480 by 720 equal to 0.6667. Exercise 1. Addition theorem. Given more than one event,